Hi, from Beaverworks Summer 2023, Quantum Software. I'm Rohan, and my teammates Audrey, Brian, and Jonathan are very proud to present to you our work on the Variational Quantum Eigensolver.
Before we get into the algorithm, let's explore some of the basics of quantum computing. You may be familiar with the concept of the classical bit, which is represented as a binary 0 or 1. Quantum computers, however, are built upon the qubit. Qubits are unique because, while they may have a 0 or 1 state, they may also be both 0 and 1 at the same time, in a special state known as superposition. Similar to the logic gates of classical computing, we are able to manipulate qubits using rotation gates. These gates allow us to put qubits in special superpositions and perform operations that classical computers could never accomplish. We are able to design complex quantum circuits by applying these gates on a set of multiple qubits. Well, if quantum computers are built on qubits, and qubits in superposition don't have a set 1 or 0 state, how do we get useful information out of our quantum circuits? This is where measurement comes in, which happens after running the entire quantum circuit. Qubits in the 1 or 0 state measure how you would expect them to, returning a binary 1 or 0. However, when it comes to a qubit in superposition, there is a probability of measuring either a 1 or a 0. Thus, it is said that the qubit collapses into a Boolean state, and furthermore, cannot be used until it is completely reset for the next circuit. So why are quantum computers so special then? Entanglement and interference. Entanglement is when the outcome of one qubit affects the outcome of another. This is achieved by applying special control gates on the qubits, sort of like the AND gate of classical computing. On the other hand, interference occurs when the waves of two qubits superimpose upon each other, either strengthening the signal or canceling it out. These concepts, unique to quantum computing, are essential to the function of a complex algorithm like VQE.
To understand what the purpose of a variational quantum eigensolver is, we first need to understand what variational quantum eigensolver means. Variational means that it uses a method of optimizing parameters to a system to get a great approximation of the answer. Quantum means that it uses quantum algorithms and hardware to compute the solution, as opposed to classical algorithms and hardware. Eigensolver in this situation means that it solves the time-independent Schrödinger's equation. Now that we know what the variational quantum eigensolver means, we can learn what it does. The inputs of a VQE are certain parameters and values along with a specific matrix called a Hamiltonian that changes depending on the molecule you are looking at. The output of the VQE is the energy of the ground state of the molecule that you put in. This can also be turned into the distance the atoms in the molecule are apart in its ground state. Now, what can we do with these outputs? There are many things we can do, especially as quantum computers improve and grow in their capabilities. Some things we can do just now are to simulate molecules that can assist in drug creation, that can help with making medicine cheaper and with less side effects. And also, we can potentially create new materials that have new and useful properties. So, why do we have to use a quantum computer and algorithm instead of a classical one? There are a number of other reasons, but some are that the calculations for large molecules and models could theoretically take classical computers millions of years, while a quantum computer could complete it in just a few minutes. In addition, what may take 1,000 qubits may require more classical storage than exists on Earth. Not only that, quantum computers are also much more accurate at getting the correct data and solutions than classical computers.
Okay, so now that we understand the basics of quantum computing and also the applications for VQE, we can know the steps to the VQE implementation. So as you can see in this diagram, the VQE algorithm is generally split into 3 steps: initialization, evaluation, and tuning. And the steps evaluation and tuning run in a loop known as the optimization loop. So first, we would need to define a matrix representation of the molecule that we're trying to simulate. And this is officially known as the Hamiltonian. And then from the matrix, we would generate a set of initial parameters. Finally, we would need to define a quantum circuit using those initial parameters. Now that the initial parameters and circuits are set up, we can move on to the variational loop that consists of 2 steps, evaluation and tuning. These 2 steps repeat until the optimization algorithm converges upon a minimum energy value. For the first step, evaluation, we run the quantum circuit using the parameters. After measuring the qubits, we obtain an expectation value that represents an estimated ground state energy. In the second step, tuning, we perform an optimization method known as gradient descent, which updates the parameters. We repeat this process until the difference between each iteration's output becomes nominal. The value that our variational loop converges to is the system's ground state energy.
In this section, I'll be covering my implementation of the variational quantum eigensolver and analyze our results to see what they mean. Here we have our pipeline of the algorithm, which Audrey presented in the previous section. This implementation of VQE is to find the ground state of a simple molecule like dihydrogen, or H2. Starting with initialization, we load the molecular data from a Markov file with information about H2. Here, there's a plethora of information, but for VQE specifically, we're going to be focusing on the fermion Hamiltonian. For step 3, we load our ansatz, our initial quantum state of H2, from this file. In step 4, we perform our Jordan-Wigner mapping, which converts fermionic operators to qubit operators, building our quantum representation of the molecule. Once we have this Jordan-Wigner Hamiltonian, we can encode the ansatz with variational parameters to have our final qubit Hamiltonian with variational parameters. So let's take a closer look at our Jordan-Wigner Hamiltonian of H2. The numbers underlined in red are our variational parameters, but what do these mean? The fermion Hamiltonian that we encode has information about particle configuration and interaction. We can convert this to a quantum state, which can be represented as a wave function. So our parameters are really just amplitudes for this wave function, which we use to describe our molecule's behavior. Here we enter the optimization stage. The first function simply evaluates the expectation energy of the Jordan-Wigner given a certain set of parameters. Our goal is to minimize the expectation energy to find this ground state. So the second method uses a classical optimizer to optimize the parameters in order to minimize this energy, finding our ground state. This chart here shows the expectation value given distances between hydrogen atoms in H2. We're going to break down what this means. After running our optimizer, we found a ground state. This ground state indicates the lowest possible energy of the molecule, and this is our most stable configuration. The goal of VQE is to find eigenvalues that find the ground state. As you can see in the code, our optimizer has found a ground state which is accurate to billionths of a heartbeat. Finally, all this code is run on a quantum simulator. But what if we were to run it on the real thing? Resource estimation tells us that it would take about 4 qubits to run the circuit, which is well within our bounds. Azure's IonQ Harmony computer has 11 qubits, so we can run this with no problems. Looking to the future of VQE, there are many practical applications for this algorithm. Starting in medicine, we can start using VQE for different drugs like Alzheimer's treatment, cancer treatment, and HIV. Well, it also, in general, VQE is an algorithm to find eigenvalues of any matrix. We also have uses in finance, like portfolio risk minimization and approximate optimization algorithms. So in general, VQE, given enough qubits, can be super powerful, creating revolutionary drugs and changing our entire finance industry as we know it. So that was our presentation on VQE. Thank you so much for listening, and let us know if you have any questions.